Go ahead.
Good morning, everyone. My name is Şevki Çeşmeci. I am a PhD student in Mechanical Engineering Department. And today I'll talk about my research topic. We have been investigating the possible ways to increase coughability of mucus out of human trachea. People having lung diseases such as asthma, COPD. COPD stands for chronic obstructive pulmonary diseases, and cystic fibrosis need to cough effectively to remove the mucus from their trachea. We mostly work experimentally, and we have our own experimental model in our biomedical lab here. The experimental setup consists basically of a flow source to generate flow, cough, and a pipeline, and flow measurement devices along the way, a computer here for data acquisition, and our model trachea here. The model trachea is basically a clear plastic tubing, a D-shaped clear plastic tubing, so that we can see what's happening inside actually. And we also make our own simulant, mucus simulant, in our lab from LBG, locust bean gum powder, and LBG powder and borax solution at different concentrations for thicker and thinner mucuses. And then we insert a certain amount of mucus here, a droplet, and then we send flow from here over the simulant, different types of flows, and then we observe the displacement of the simulant after each trial experiment. We have a ruler here and also a camera to record each experiment. We also, as I said, we send different types of flow patterns, like a single cough or a triple cough, like or cough with oscillations, a single cough with oscillations. Single cough would be, let's say this is volume, flow rate, and this is time. A single cough would be a cough pulse, something like this. A triple cough would be something like this, cough, 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 and a cough with oscillations would be oscillations superimposed on top of this single cough pulse. And fourth type is triple cough with oscillations, vibrations. So a cough with oscillations would be something like this, and triple cough with oscillations would be. We also change the angle of inclination of the model trachea here to see its effect on overall displacement of the mucus. So we saw the higher the inclination angle here, the higher the displacement of the mucus. And also the superimposed oscillations gave higher displacements at all angles. At all angles. We change angles from 0 to 45 degrees at increments of 15 degrees. Of course, there are other parameters playing a role here, such as surface properties of mucus simulant, adhesivity, surface tension, contact angle. You have a droplet of mucus simulant, ensure you have contact angle here and surface tension and adhesivity, which plays a role here, a key role here. Because the higher the adhesivity is, the more force you need to apply to pull this out of the base. So as a future work, I'm trying to, I'll change these surface properties, and I'll try to observe the effect of these properties. And after collecting enough data sets, I am planning to do a non-dimensionalization to see the most dominant effect here, what parameters are most effective here, most significant here in this process. Yeah, that's all about it. Yeah.
I mean, for what purpose your instrument or your developed system will be used?
Say it again.
For what? I mean, where you will apply your system?
My system, okay. So today, in practice, in hospitals, technicians using cough assisting devices. We have one in our lab from Philips. So basically, our work here will help them to improve their devices. The devices that we have in our lab just uses an inhalation and an exhalation. But as I said, we're trying oscillations here. Maybe that machine will produce oscillations and it will make the cough mechanism more effective. Or in mucus-wise, we'll change some properties of mucus. So far, we played with bulk properties such as elasticity, viscosity. But as I said, from now on, after my research, literature research actually, I'm planning to change the surface properties such as surface tension, contact angle, adhesivity, or cohesivity.
How do you measure contact angle of your surface here? Well, the droplet or whatever.
Yeah, I didn't measure it actually, but you can, for example, contact angle is because of surface tension and the wall. For example, you have a small tube here, and you'll have capillary rise, and this will be your contact angle. So when you come close enough to the tube, and you can just take a picture, or you can record a video, and then you can analyze afterwards. Actually, this is my way. I don't know how they measure it in practice, but this would be my way.
How do you do that? Doesn't the material of the wall make a big difference when you're calculating the contact angle?
Yeah.
So wouldn't you have to have a trachea or something like that? And how
Or
would you
vary
see-
your surface.
How would you see through that to be able to visually see what that contact angle is? Is there a method for that?
We haven't done this yet. This is my feature work, but actually the trachea here is not resembling the actual trachea. So it has a rigid wall, but actual human trachea is flexible, you know. So this is a progress. So first a simple trial, and then we'll enhance the model later on. Any other questions?
Okay, thanks.
Mm-hmm.